module 5 till module 10. That includes the conversions from assembly instruction to machine code. So since you didn't have any such conversion in the midterm, you can expect to see such conversions in the final. Then we talked about procedures, we talked about stack recursion, and finally we concluded with GPIOs. So if you have any problem regarding any particular topic, we can go through that first. If anyone doesn't have a problem, like a specific topic or something, then we would just do a general review and kind of discuss what could come up from the chapters. So this from this you should see some questions in the final. Now, um, as you've seen in the mid, there were questions from almost all aspects, right? So there's nothing that you could really skip. There were questions from barrel shifter, addressing modes, um, what else? Hardware components, flags, right? So everything is kind of important. So from this chapter, we started talking about instructions and that they could be represented as data. So because instructions could be represented as data, um, it made it possible for us to use the same memory technology for both, right? So same memory technology as in caches. So you use caches to store data or numbers. Similarly, you can use caches to store instructions because instructions are nothing but a series of numbers like data. Everything has a memory address, and so branches make use of memory address, as we know, in order to jump to a particular label or a target. It needs an address, right? So every target or label has a unique address, and branches make use of that in order to jump to those addresses. The other question, I think it was a true false, right? So C pointers, memory addresses, um, also the significance of program counter and instruction register. You had that in your midterm. Probably the things that already came up in the midterm won't be there in the finals, okay? So you had questions related to the hardware components of ARM. Of course, that's not part of this final syllabus. And you saw questions regarding flags, program counter, instruction register, RISC and CISC, the architectures, um, constant multiplication, constant division, addressing modes, barrel shifter, branches, right? And then a coding problem. So the final would be kind of similar. Make sure that you revise the slides well. You don't skip anything from the slides. Okay, and you might expect some MCQs and true false like the midterm. Should be mostly focused on the theory. And machines are backward compatible, meaning that they want to run the older programs They want the older instructions to execute in the latest PCs as well. So instruction sets evolve over time, right? Because you have more and more instructions being added to the instruction set. Why is that? That's because you now want to achieve more. Okay, you want to do more complex tasks. So that's why you need new instructions. So the instruction set keeps evolving over time. I think you had a question in the midterm regarding thumb instructions. Okay, so all of this we saw the conversion from instruction to machine code. All of that would be there. So you could expect some questions from here, and you'd be given the necessary data. So you'd be basically given the ARM reference card. Okay, so the ARM reference card looks like this. So you would have this table or this opcodes, this fields, all of this. Okay.
Sir, slide 3 take to sorry,
Yeah, what's that again?
sir, ARM card instruction যেটা ছিল স্যার slide 3 টা স্যার
Okay, slide 3. Okay. Yes.
স্যার এই যে এখানে যে স্যার আপনার 4 নাম্বার বিটটা স্যার একবার 1 থাকতেছে sometimes and sometimes there are 0 স্যার এই রিজনটা স্যার একটু
Okay, so there are two ways that you can apply this shift, right? You can see a shift field. So you can apply a shift to this register Rm, right?
yes sir
To the value in Rm. Now you can apply this shift in two ways. You can either apply the shift manually. That's when you have this left configuration, the one in the left. You can see that bits 7 to 11, right? These
yes
bits
sir
are,
5
how many bits are there? 7, 8, 9, 10, 11. So 5 bits. So
yes sir
this is a 5-bit unsigned integer that you can use to use as the shift amount to apply shift on the value in this register Rn. Okay, so this you use on the left. This is the one you use when you have to when you manually apply the shift. But on the right, you use this whenever you don't want to manually apply the shift, but you use another register RS to apply the shift. So RS is another register. It's called the shift register. It could be um, just excuse me for a minute, okay? Yeah, sorry for the interruption. We're discussing. Can you hear me?
Yes, sir.
Okay, so we were discussing this slide. So this on the left is to manually apply the shift, and on the right you make use of another register to apply the shift. You take this shift register, and it has 32 bits, but we only use the bottom byte. So that means the last 8 bits. So you whatever the value is in the last 8 bits, that value is used as the shift. Okay. So that is manually, so that is making use of a register to apply the shift instead of writing the shift directly. Okay. Or
Yes, sir.
applying the
Okay.
shift directly. And you would have this thing given. This is for the condition field. Yeah. Yeah, so whatever you see here would be given. Okay, it would be exactly the same as the 6 slides. Okay, this one is not there in the arm reference card, but um, let's say if I can include this, if I can include this, I think that would be better. But if I don't include this, probably there won't be any questions related to this. Okay, so this is just making use of the pseudonyms. And we know that there's only a limited space that is assigned for the constants, right? Because the entire number or an entire instruction is 32 bits, okay? And only 8 bits are reserved for the constant. So in order to extend it, we need barrel shifters. And we discussed the use of barrel shifter and the significance of barrel shifter. And we saw the shifts and rotates. So this, excuse me. Distractions today. Okay, so this shifts and rotates. Right? So this was covered in detail in module 4. Um, here you just need them for some of the instructions, right? So some of the instructions might have LSL, LSR, ASR, or ROR. So that's why you have this slide. And we discussed different examples for data processing instructions. All of that is important. You would want to revise that. Any problem understanding any of the instructions that we discussed? Any of the examples? Then we talked about branch instructions. Right, how we make use of this formula. How the offset helps us jump instructions, how many instructions it can jump, how many words, how many bytes it can jump, and the conversion from word to bytes whenever we make use of this equation. Right? We saw all that. So this we updated. So when we don't take the branch, this is how the program counter is updated. I hope you can hear me. So
Yes, sir.
if we don't take the branch, this is how we update or increment the program counter. Is just PC equal to PC plus 4, where you just move or you just execute the next instruction, okay, the immediate next instruction. But whenever we take the branch, we add this term offset times 4. Why are we doing offset times 4? Because offset is in terms of words. We multiply that 4, but we multiply the offset by 4 in order to convert it to bytes. Okay, and we know that we need to make this conversion from word to bytes so that we can make use of this entire equation, right? Because memory address is always in terms of bytes. Okay, so you would want to convert the offset from words to bytes and then add it with PC plus 8. Why PC plus 8 and why not PC? We discussed that it is because of pipelining, right? It is because of the hardware. Whenever you're executing a particular instruction, actually, the next instruction is being fetched. Okay, so I think we could go over that again in short. So there are different stages in a pipeline. First is the instruction fetch, instruction decode, and execution. So let's say we are executing instruction 1. That means instruction 2 is in the decode stage. We are assuming that they are simple RISC instructions that take one cycle to execute, or one cycle to process. Okay, so instruction 2 is in decode stage and instruction 3 is in the fetch state. So whenever you're executing instruction 1, actually the third instruction is in the fetch state. So that's where PC plus 8 comes into the picture. If this instruction 1 has an address of PC, instruction 3 would have an address of PC plus 8, and we add the offset with this PC plus 8, right? Because that's the instruction that's being fetched. That's the last instruction in the pipeline. Okay, so instruction 3 has an address of PC plus 8, and um, the offset is calculated with respect to the instruction that is being fetched. So why is this necessary? It's we always want the pipeline to be full in order to maximize the instruction throughput and reduce any pipeline stalls. Okay, so this is done to maximize the efficiency of the system so that we get enhanced throughput. So that's why. Okay, any confusion regarding this? Why we add the offset to PC plus 8 and not PC? If you want a detailed uh, understanding or a better understanding, you could always refer to this document. It has all of that in detail. Okay, here so you can go through this, but that's the basic idea, that we add the offset to PC plus 8 due to pipelining, and it this helps maximize instruction throughput and reduce pipeline stalls. So this bullet is kind of important. By using PC plus 8, the processor is fetching the instruction that comes after the next instruction in memory, effectively assuming that the branch is taken. This helps keep the pipeline filled with instructions even if the branch instruction turns out to be taken. Okay, any questions regarding this? Why we add this to PC plus 8 and not PC? So it comes from this concept that whenever you're executing instruction 1, your instruction 3 is in the fetch state, and your program counter actually stores PC plus 8. Okay, whenever you're executing instruction 1. So that's why this offset is in terms of PC, and PC is actually PC plus 8. Okay, whenever instruction 1 is being executed. Now we looked at some examples involving branch instructions. So this could come up in the exam. So I haven't really started preparing the question yet. I would do that soon. But it would cover these things, so nothing out of the syllabus. Everything would be there from the slides. And what do we use if-else for branches for? We use them to implement if-else statements and loops. Right? So whenever you have a loop, you would want to convert that to if-else statements and then implement those if-else statements using branches. And how to handle cases if the offset is too large. You would want to answer these 3 questions, practice these 3 questions. Finally, we talked about data transfer instructions, which involves loads and stores. Right? We talked about the addressing modes. We discussed a few examples related to loads and stores. And that was it for this chapter. Okay, any questions from this module?
So data transfer module পার্টটুকু থেকে কি কি দেখা লাগবে?
One more time.
ডেটা ট্রান্সফার পার্টটুকু থেকে কি কি দেখা লাগবে?
Data transfer, you would want to know how you would fill up these fields, all these different fields, right? Offset, destination register, base register, condition fields, intermediate, pre or post indexing. Then if it's a byte transfer, if it's a load, if it's a write back, if you're adding the offset or subtracting the offset. So you'd want to know how to fill up these fields. If you're given an instruction, either a load instruction or a store instruction, you would want to know how to convert it to machine code. Okay, so that's one thing. Also, you might be asked about the addressing modes. Um, Also, you might be given something like a memory map where you have several memory locations, and you might be asked where does data go, or from which location do you read, stuff like that. Okay.
Okay.
Or you might be given something. Um, so you've seen how a memory map looks like, right? So let me just show you here. So something like this, right? So this, let's say you have several memory locations, and based on some given information, you might be asked to fill up the space with data, or you might see some data here and you might be asked like what would be the output. Okay, something like that.
Oh,
If you saw the video on addressing modes, you saw like something like this, right? If you saw the video on addressing modes, they have something like this, different memory locations, and that's filled up with data. So how to work with those, okay, data and memory locations. Right, any other questions from module 5? If not, let's move to module 6. So here we talked about procedures and the standard convention. So we would always want to follow the standard convention. What was the standard convention? You make use of R0 to R3. So this R0 to R3, their pseudonyms are in terms of A. Okay. So this registers, their pseudonyms are in terms of A. So they're called A1 to A4, I think. Yeah, A1 to A4. Okay. So this registers are called A1 to A4. Those are the pseudonyms, and A stands for argument. So this registers are basically used to pass on arguments and pass on the output, okay, return output. So you would want to make use of this registers when passing on arguments and the return output. Similarly, the ones you see next, R4 to R11, their pseudonyms are in terms of V. V stands for the variable registers. They're called the variable registers because um, they hold the value of the local or global variables. Okay. So whenever you're dealing with variables, you would want to make use of this registers to store those variables. So we saw an example. What was the example? In the example, we had a main function, okay, and the main function was calling another subfunction, subroutine sum. So this is the subroutine that you see, and then we tried to implement this using assembly, right? So this is how we tried to implement it using assembly. You see the conversion from C to assembly. And we saw the use of BL and BX instructions. So BL is whenever you want to jump to a particular label or target, as well you want to update the value of the link register so that you can return to the link afterwards. Okay. So, or what you could do is manually move the address to the link register and then do a simple branch B instead of BL. You could do a simple branch to the label, and then after you're done executing that subroutine, you return using BXLR, you return to this address 1016. Okay, so that's the immediate next instruction after the branch instruction. Any question regarding this concept of BX? I think you saw this during your labs as well. So why you use BX here is to return to somewhere in the code, right? Return to some place in the code as indicated by the value in this LR register. Okay, so these are two alternate ways. You can manually update the address in the link register, or you can make use of the BL instruction. So BL instruction automatically updates the address in the link register. So this BL instruction has two functions, right? It helps you branch to a particular label, and it updates your link register to store the address of the next instruction. And this is the syntax for BX. BX is always followed by a register. It's never followed by a label. So BL stores the return address in the link register, and this BXLR jumps back to that address in the link register. We saw an example of a nested procedure where this sum square function was actually calling another function mult from within. So this is an example of a nested procedure, and we discussed that in a nested procedure, the return address for sum square is actually lost. So the sum square would want to return an output to the main function, because the main function would be calling the sum function, or some other function could be calling the sum function as well, right? So whichever function calls the sum square function, it has to return an output to that caller function. But it is not whenever this kind of a nested procedure is there, or a nested function call is there, the return address is actually lost. So you would want to store that return address somewhere before making the nested procedure call. Okay, so that's the summary of this. And we saw the type of regions there are within the SRAM. Okay, what are the regions within SRAM? You have a space for stack, space called stack. You have heap. You have a space for the static variables, which are the global variables. So those are the different sections you see, exactly like this. So you have a space reserved for local variables and procedure calls. That's called the stack. For global variables, you have a space assigned. That's, you can see it has been denoted by the term static. The space is reserved for the static variables, and you have the heap for the variables whose size changed during runtime. So for dynamic variables. Okay, and at the bottom you have this code. So this is actually not part of the SRAM. This is your instruction cache, or you could call it flash memory. Okay, or flash. This is for the program. So whenever you have to deal with nested procedures, you extensively make use of the stack. Okay, because you would want to store the return address to the stack because it gets lost whenever you're calling another function, right? You're calling a nested function. So you use the stack pointer, you increment the stack pointer to create some space on the stack. Why do you increment it? Because why do you increment and not decrement it? Because whenever you increment it, you're creating space, because this is ARM has a descending stack, right? ARM has a descending stack, which is why you do something like this to create space on the stack. And see, using this line, you're actually storing the return address. Okay, because you know the return address would get lost whenever you're doing this BL mult. This BL mult is this is used to call the mult function. The mult function, as you saw, was a nested function, right? So whenever you do something like BL mult, you're calling the nested function. Your return address is lost, so you would want to store the return address, your stack, and you would want to store any variable that you need later, right? So in this case, if you see, you need this variable y. So whatever output is produced by the mult function, that output is added to this variable y. So besides storing the return address in the stack, you would want to store the value of y in the stack as well. So that is being achieved by the third line. So this third line, it stores y in the stack. And after you do the function call, you move to this label, mult does its operation. Then you have this bxlr, and you return to the next address after the BL call. Okay, so you return to this LDR. After you return to the LDR, so what are you doing through this instruction? You restore y. So you saved y to your stack. Now you restore your y. Okay, because now you would need that y for the calculation. You restore y in register R1. Okay, and you add that value to whatever was the output from the mult function, and you then get the final result R0. This is the result for the sum square function. Okay, so now this R0 would be returned to the main function, because if assuming that the main function was calling the sum square function. And also you can see that the return address is being loaded to the link register using this instruction. This line is incrementing your stack pointer. So this basically restores your stack to the original place. Okay, we know that we have to always restore the stack to its original place before leaving the function. So after we are done restoring the stack to its original position, we then have this bxlr, through which we move to the main function. Okay, that was calling sum square. So this kind of the first part is the push. We saw what are push and pop instructions. So the first part represents push. It's the backend code for a push, and then you have this pop. So what's push? Whenever you push something to your stack, right? That's a push. Whenever you retrieve something from the stack, that's a pop. Whenever you store something on the stack, that's a push. Whenever you retrieve something from the stack, that's a pop. Okay. So any questions regarding any of the lines here in the slide? So this kind of gives you the steps, right, that you need to follow while making a procedure call. You save the necessary values to the stack. Any arguments that you need to pass on, you need to assign those arguments to certain variables. So you make use of the argument registers here, A1 to A4. Okay, you make the BL call. Then you restore values from the stack. You restore the stack pointer, and then you finally use BXLR to return to the main function. Okay. There are some rules you need to follow. Rules as in the standard conventions. So we have already discussed that. Standard conventions. And so this bullet is kind of important. It says, whenever callee returns from executing, the caller needs to know which registers may have changed and which are guaranteed to be unchanged. So there are some things that are guaranteed to be unchanged, right? Whenever a callee returns from executing, what are the things that are unchanged? What are the things that are guaranteed to be unchanged? So the stack pointer is guaranteed to be unchanged, right? Because you always restore the stack pointer before making the function call. So the stack pointer is always guaranteed to be unchanged. What else is guaranteed to be unchanged? The variable registers are guaranteed to be unchanged, because you see, you always have to restore them if you change them. However, these things are not guaranteed to be unchanged because they can change. So every time you make a BL call, the LR register is updated, right? So they can change. The argument registers are called the volatile registers. So volatile means their values keep changing frequently. So argument registers can change as well. So they are not guaranteed to be unchanged. Okay. Right. So for the variable registers, if there is any chance that the callee function would garble up the values in the variable register, you would always want to store these values in the variable registers to the stack, and then before returning, you would want to restore those values from the stack, so that these variable registers contain the original ungarbled up values. Okay, so remember we discussed this. Similarly, for this argument registers, if you need these values later, you would want to store them to the stack. Okay. For example, in the previous example we discussed here, we saved the value of y, right? We saved the value of y to the stack. Why did we save the value? Because we would need that later, right? So for this intermediate calculation. So save any temporary registers before making the function call, and you save any save registers before garbling up their values. Right, so why do you need to store the values in the temporary registers? If you need them later, you need to store them to the stack. For the save registers, if you think they would get garbled up, you would want to save them to the stack. Okay, and only the ones that are being used, they need to be stored to the stack. Not all the registers need to be stored to the stack. So this is kind of a general summary of what we already discussed, that This is how you decrement the stack pointer and create some space in the stack. After you have some space in the stack, now you are good to store different things in the stack. Okay, you can store the return address. If it's a nested procedure call, you need to store the return address because it is lost whenever whenever calling a nested function. Also, you might need to save other registers if you're needing their values later, or if the values could get garbled up, right? So once you're done with the nested function call, you restore the values from the stack. Okay, you restores any variables that you saved, you restore the return address that you saved, and then finally you increment your stack pointer so that your stack pointer points to the original location. Okay, and then you do this bxlr to return to the main function, or whichever function is calling the function. Then we saw this code conversion. This was simple. First part was a main function which was calling the same function but using different arguments. Okay, and you're storing the result in different variables as well. A mapping was given, right? We converted that to assembly. So here you can see the main function is calling the mult function, and the mult function looks like this at the bottom. It has two arguments, mcand and mlear, and you can see the operation that it does. It declares an initialization, initializes the variable product, and then makes use of a while loop. While this condition is true, this is what you do to the variables. Okay, this is what you do to product, this is what you do to mlear, and you continue this until the condition doesn't become false, and then you return the product. Okay, product is the output. You return this product to the main function. So we saw it was a simple conversion. Okay, you could expect to see simple conversions like this. Okay. So it says main function ends with done. So not bxlr. So there is no need to save this lr to the stack. So what it says, when do you need to save lr to the stack, or when do you need to save lr, is whenever you have a nested function call. That's when the return address gets lost, and that's when you need to save the value of lr to your stack. Now, let's say the main function, we are talking about the main function. The main function doesn't have to return the value to somewhere, right? Because no one calls the main function. The main function is always calling other functions. So the main function doesn't need to return something, return a result to any other function. That's why within the main function, you don't see something like a bxlr, because it doesn't have to return somewhere. Okay, and because it doesn't have to return somewhere, you don't need to save the lr to the stack for the main function. And all variables used in the main function are saved registers. Saved registers means the variable registers. So there is no need to save this onto the stack. When do you save saved registers to the stack? Whenever there is a chance that the callee function would garble up their values. So the main function is never a callee function, it's always a caller function. So there's no chance that, but there's no problem with the values being garbled up. Okay, because no one actually calls the main function. This could be a bit tricky if you don't understand. So do you have any questions regarding this argument? Volatile registers, temporary registers, save registers, they have different names, but some of that mean the same. Right? So the argument registers are called the volatile registers. They're also called the temporary registers. And saved registers are called the variable registers.
So I have a small confusion.
স্যার
What's
নেস্টেড
that?
প্রসিজারটা কি এক্সপ্লোর করা যায়?
Nested procedure?
নেস্টেড প্রসিজারটা কি একটু বাদ দেওয়া যায় সিলেবাস থেকে? মানে কনফিউজিং।
So, nested procedure is part of the syllabus. It would be there. Which part is confusing regarding nested procedure? I think you just saw one example for nested procedure. This was the example. This is the example. We just saw one example. This is the one. Which part is confusing?
Yes, sir.
Sir, during the exam, should we follow the convention like if it's specified in the question, or should we allowed to use any?
So it's always better to use the convention. Okay, so try to use the convention during the exam.
Oh, so it's better, but the mark will be allocated to it, sir?
So I'm not sure about that, but it's always good to use the standard convention and try to follow that. Okay.
Yeah, thank you, sir.
And regarding nested procedure, we just saw this one example in class. Okay, so it's a simple one where you had a sum square function and you are calling another function which is the mult function from within. Okay, so what's the confusion here? What you need to take care of is the return address. The return address, now what's the return address? Or return address to what? Return address to the main function, because the main function would be calling this sum squared. Okay, so the sum square function needs to return its output to the main function, right? Because the main function is calling the sum square function. So the sum square function needs to return its output to the main function. But because you have this call to mult function, the return address is lost. Return address to the main function is lost. So that's why you save that return address to the stack before making the return. That's one thing you have to be aware of. Another thing you have to be aware of is what are the variables you need to store. So here you need to store this variable y because you need this y later for the calculation. Once mult returns a result, this y needs to be added to that result to produce the output of the sum square function. So you want to store y because you need the value of y later. And y was stored in a volatile register. So anything in the volatile registers that you need later, you would want to store that to your stack. Okay, so that's about the volatile registers. How about the saved registers? Saved registers are the variable registers. So they are expressed in terms of V. And when do you need to store them? When, let's say, you are a callee function, and there's a chance that the callee function would change the values in those variable registers. Okay, so you don't want that. Why you don't want that? Because the main function would be using those variable register values. It would be looking for those old values. So if the callee function garbles up those values, then it's a problem for the main function. So that's why if there's a chance that the callee function would garble up those values in the variable registers, you would want to store the old values in the variable registers to the stack before them getting garbled up. Okay. Okay, this was the assembly conversion for the bottom part of this code. So basically we have two parts here, the main function and the subroutine. So we saw the code conversion for them. And from this example, what did you learn? So there are a few notes. It says no BL calls are made from mult. So if you see this mult function at the bottom, it doesn't call another function. So this is not an example of a nested procedure. Okay, so this is a simple function. It doesn't call another function. Okay, so here the return address won't be lost. So you don't need to store the return address to your stack. Right, so what it says is no BL calls are made. So no function calls are made from within the mult function. You don't use any save registers. So save registers are the V registers. If you see the code, you would see the code doesn't make use of any V registers, right? It only makes use of this A registers. It doesn't make use of the V registers. That's why you don't need to save them to the stack. Only temporary registers or the volatile argument registers are used for the intermediate calculations. You could have used save registers instead of the temporary registers, but if you did use save registers, you would have to save them to the stack. It says A2 is modified directly. So probably you don't need the value in A2. That's why it was modified directly. Instead of storing a copy of the old value, it was directly modified. So you don't need that value of A2. That's why it was done. And result was put in R0 before returning. So this is following the standard convention. So in conclusion, this is the summary that functions are called using BL and return using BXLR. Stack is your friend. Use it to save anything you need. Just be sure to leave it the way you found it. Right? So what it means, you create space in the stack by decrementing your pointer, stack pointer. But after you're done using the stack, you have to restore the stack before leaving the function or before returning to the main function. Okay, you be sure to leave it the way you found it by now incrementing the stack at the end. First, you decrement the stack in order to create space in the stack. Once you are done using the stack, you now increment the stack, so you now point to the original location before returning. Okay, any questions regarding this? Stack recursion, we saw the data structure. It follows a LIFO structure, last in, first out. Whatever data